Okay, so to study the magnetic interaction, it can be very tricky because it's not just the interaction between South Pole and North Pole. Whenever you get a magnet, you get both of them. So when you put two magnets together, you must just study interaction between South, interaction between North, interaction between South and North. So it can be really complicated. So to study this type of system, I'm going to look at this problem in a very specific angle. I'm gonna start with magnetic field. So my logic is, instead of just jump into the magnetic force between two magnets, why don't I just take one magnet and study the magnetic field generated by this magnet? And then when I put another magnet into this field, this magnet will feel that field, and then this has the magnetic interaction, which is the magnetic force. So first, I'm going to following along this line, I'm going to first study the field, and then study how a magnet feel a field. Okay. So in this video, let me introduce you what's a magnetic field look like. It's kind of like electric field, but of course it's gonna be different because North Pole and South Pole are together, unlike a charge can be separated. So let's see. This is a fact simulation where you can see a bar magnet. If I put a compass around it, you can see the compass, the red one is the North Pole and the white one is the South. You can see the North Pole attracted to the South. Okay. If I put it here, you can see the white is attracted to the North, right? So now imagine that you have hundreds of compass needles on this screen. And this is, then you will observe a pattern show up around this magnet. So if I draw down this pattern, so if I follow along the line, draw down the pattern, it probably looks like something like this. Okay. So the yellow line that I'm drawing here is we call the magnetic field line. Magnetic field, I will use B to represent a field. So B line means magnetic field line. So if I want to see what's the magnetic field at this position of the compass, okay, then you can see I will definitely need a magnitude. And besides the magnitude, I also need a direction, right? Because this magnetic field will align a compass in this direction. So I also need a direction to tell people. Like if we put a compass here, what's gonna happen? Remember that we said that for each magnetic moment, for each magnet, we use magnetic moment, and the direction for that magnetic moment is pointing from south to north. So at this position, we will say magnetic field is this way, pointing from south to north. So because of that, so now we will have a new rule. It's just conventional definition. So we will say the direction of magnetic field outside of a magnet is pointing from north to south. So you can see this is the north, this is the south. So the magnetic field will pointing from this way. So, oopsie, it's out here. So say for example, if I pick a compass here, when I put a compass here, you can imagine this compass will want to pointing to the right. And it does, right? It's pointing to the right. So that tells you the direction of the magnetic field. And if you want to know the magnetic field strength, you will need a magnetic field meter to measure the strength. So for example, at this position, it's 1.34. And at this position, it's 0.14. So you can see like away from this magnet, the magnetic field will decrease. And here's one more thing that you may notice is that you can also read the magnet of the magnetic field on this field line by looking at its density. So what I'm saying is, in this area, you can see the density line is higher. In this area, there's almost no field line, and there's a lot of line here. So because it has a higher magnetic field lines, you can imagine the magnetic field will be stronger at this location compared to this location. And you can check it with this field meter. You can see it's stronger here and weaker here. So in some sense, it's a very similar property compared to electrostatics, compared to electric field line. The density of the lines suggests the magnitude, while the direction is purely determined by the polarities. And in this case, it's going from north to south. Okay, and so this is one magnetic field, what the magnetic field looks like for a magnet. Now what if, how about this? In this case, what I have is, you can see that I have a battery. So let me clean this up. So you can see I have a battery here, right? When I have this battery here, and then the battery is connected to the positive is coming here, the current will keep going. So what you're seeing here, this is electrons flow. So the actual current will be in the opposite direction. But anyhow, once you have such a running current wire, and then you put a compass around it, you see the compass will interact with your wire, your current as well, as if there was a magnet here. So now what if we put hundreds of compass here? Then you can see this compass, they also show a pattern. But wait a minute, don't you feel like this pattern, it looks very similar to this pattern? But now we can follow this pattern and draw the magnetic field line. And it's pretty much exactly the same as the bar magnet. So this kind of shape of current basically behave like a bar magnet. And if this behave like a bar magnet, and because we just did a side-by-side comparison, right? So you can see that this end is basically like a north pole. This end behaves like a south pole. So that's why electric field is pointing from the north to the south. We can put a compass around, and again, our field line will faithfully tell us the direction of like where this compass should be pointing at. But now we have something very interesting. If we look at this as a magnet, let me clear up the field so it looks it doesn't look so busy. So if we now we look at this solenoid as a magnet, and then when by putting this compass in the center, you can see it's pointing to the right. And we know pointing to the right means the field at that point should be going to the right. So now I'm going to, so if now I continue my field line, we know this field line, it does not stop when it reaches the wire. It will actually continue going through, it will continue going through this loop and then come out and form a closed loop. In the direction of field line, we'll just follow along it. It will be going to the right. So basically, if we carry this idea over to the bar magnet, you will see this. You can see the same thing. Okay. So now let me show you the field line. And if we show the field line inside the magnet, this is what you will see. So if I want to draw a magnetic field line here, you can see this pattern will actually come out of the magnet, go around, and then come back and form a closed loop. So all the field line, all the magnetic field line are actually all closed loop. And the direction is going from north to south outside of the magnet, but inside is going from south to north, like a magnetic moment. And we get this idea from the electromagnet, because the electromagnet is hollow, so you can literally put a compass in the center. All right, so this is what a magnetic field line would look like for a bar magnet and for the solenoid. And magnetic field line is kind of like an electric field line where the density suggesting the indicating the magnitude, while the direction is determined. We just say the direction is going from north to south outside of a magnet and south to north inside of a magnet. If you're not sure what's a magnetic field line, the direction of a magnetic field line, you can always put a compass. You can always put a compass on the path, and where the north, where the red is pointing at, will tell you the direction. I'm just gonna give you a summarized slide on magnetic field. Magnetic field is a vector. It's a field created by a magnet or electromagnet. To describe a magnetic field, you need direction and strength. We use the symbol B with the arrow on its head to describe it. The unit for magnetic field is Tesla. Yeah, it is the Tesla, shorted for T. Some people or some researchers, they will use Gauss, G, to represent, as another unit, but the SI unit is Tesla. And this is pretty much what we just talked about. By connecting all the direction of the compass, we can find a field line. The field line is going from north to south outside of the magnet, but from south to north inside the magnet. So it forms a closed loop as is shown in the C picture. All right. And before we go ahead and talk about how to calculate magnetic field, like strength-wise, and I want to tell you a few notations. In this unit, usually before people have trouble with physics, the first difficulty for most people is three-dimensional imagination. Because magnetic field, when we talk about magnetic field line, like it's not just two-dimensional, up, down, left, and right. It's usually up, down, left, right, and away from you and towards you. So it's gonna be a three-dimensional. So it will be a little bit hard to describe. To make sure our communication, is smooth later, I want to introduce a few symbols. So first, we will still use left, right, up, down arrows as shown in the picture, which you are familiar with. But I will also use into the plane and out of plane. I'll use this two symbol. So when I draw this symbol, like where a circle and the tail of an arrow, this means the arrow is shooting into the plane. So the arrow will be shooting into the plane means it's shooting away from you. So you only see the tail of this arrow. And if the direction, what I want to say for the direction out of plane, then that is a direction you will see the head of the arrow shooting out, which is a dot, like shooting at you. So that will cover the direction like out of plane.